We are now going to make an introduction to transition probabilities in radiative processes. We know that these processes involve the emission and absorption of light by materials, and that is precisely what spectroscopy studies. Spectroscopy is the analysis of the radiation emitted or absorbed by atoms or molecules. We can say that spectroscopy began with the work of Isaac Newton back in 1666 when he passed a ray of light through a prism and observed that the light was made of different colors. The description of the distribution of the different wavelengths and their respective energies is called a spectrum. A first distinction that we can observe from the spectra is between the so-called continuous spectra, the discrete ones, and the absorption ones. When sunlight or light from a dense material is analyzed, a continuous spectrum is observed. A discrete spectrum is obtained when light comes from a hot, low-pressure gas. This spectrum is made up of thin lines of different colors, and the absorption spectrum is obtained when sunlight, for example, passes through a cold gas. The transmitted spectrum shows black lines above the colored spectrum of white light. The old spectrographs used the prism as a dispersive element. Today we have diffraction gratings as dispersive elements that allow us to build spectrographs with high resolving power and that can cover practically all regions of the electromagnetic spectrum. Within the emission spectra we can clearly distinguish three types of them. Discrete spectra, as we have already said, are made up of fine lines, band spectra, and continuous spectra. The first of them is generated by gases at low pressures and high temperatures, or by elements that have only one type of atoms in their composition. It is important to note that each element in the periodic table emits a discrete spectrum when it is at high temperatures. In the band spectrum the lines are grouped in a special way and it is generated by the emission of materials formed by molecules. The continuous spectrum is generated by dense materials made up of many types of elements and high temperatures. We can say that each element or compound has its characteristic spectrum, and the measurement of the wavelengths and their intensities allow the identification of the elements as well as their proportion within the sample. The difference between the different spectra is clearly seen on this slide, and this fact makes spectroscopy a powerful tool for the analysis of the different elements present in the sample. For elements to emit electromagnetic radiation in the visible region, they must be at high temperatures, and this causes their atoms to be in excited or ionized states. This state of matter called plasma. Plasma is a gas where a fraction or all of the atoms that compose it are ionized due to its high temperature. The plasma considered as a whole is electrically neutral, and the ionic charges are equal to the number of free electrons. Plasma is considered the fourth state of matter, since more than 99% of the known matter in the universe is in a plasma state, for example stars, nebulae, interstellar gas, etc. The slide shows the entire process that occurs in a solid when a high amount of energy is delivered to it, for example by the impact of a high-power laser pulse. The ablated matter reaches temperatures in the order of 10,000 degrees Kelvin in a few nanoseconds, with typical electron densities of the order of 10 to the power of 18 electrons per cubic centimeter. When we observe the sun, lightning, the flame of a candle, etc., we see matter in a plasma state, obviously at different temperatures. Due to the characteristics of plasma, it is a good conductor of electricity since it contains free charges and is also very sensitive to magnetic fields. To understand the radiative processes that occur within an element, we return again to the emission spectra. The simplest spectrum that exists in nature is the spectrum of hydrogen, which consists of a regular series of spectral lines, and its wavelengths can be expressed through a simple mathematical expression. In 1885 Balmer proposed an empirical expression to calculate the different wavelengths of the visible spectrum. In 1890 Rydberg proposed an expression to calculate the wavelengths belonging to the different series observed in both the ultraviolet and infrared regions. To understand why hydrogen emits this way when excited, we need to review some historical facts. In 1897, Joseph John Thomson discovered the electron and proposed a model for atoms where the electrons were embedded within a mass of positive charge. In 1911, Rutherford measured the scattering of a beam of alpha particles hitting a thin sheet of gold. As a result, he proposed a model in which the atom consisted mostly of empty space, with all of its positive charge concentrated in the center of a very small volume, surrounded by a cloud of electrons. It is, therefore, a physically unstable model, from the point of view of classical physics. Niels Bohr in 1913 established the following postulates to explain the spectrum of hydrogen. First, electrons revolve around the nucleus in circular orbits under the influence of the Coulomb attraction between the electron and the nucleus and obey the laws of classical mechanics. Second, electrons can only revolve around the nucleus in those orbits where the angular momentum of the electron is an integer multiple of Planck's constant divided by 2 pi and n is an integer called the principal quantum number, which is 1 for the first orbit, 2 for the second, etc. Third, an electron moving in an allowed orbit will not radiate electromagnetic energy despite being constantly accelerated. Fourth, when an electron passes from an outer, higher energy, orbit to an inner, lower energy, orbit, the difference in energy between the two orbits is emitted as electromagnetic radiation and absorbed as it passes from an inner orbit to an outer orbit. In this theory, the link between the spectrum and the atomic structure is established. With the advent of quantum mechanics and the discovery of electron spin and nuclear spin, it became possible to understand complex spectra such as those belonging to elements with many valence electrons. It should be noted that the values of the energy levels of the hydrogen orbits calculated through the Bohr theory are the same as those calculated with the Schrödinger equation, and in both cases the energy levels depend only on the principal quantum number n. The figure shows the energy levels and the transitions between them that give rise to the different series of the hydrogen spectrum. Now the process of emission or absorption can be described in terms of the electronic structure. An important fact that is observed is that, for example, an electron that is in level 4 can make a transition to level 1, or it can make a transition to level 2 and then to level 1, or it can also make a transition to level 3, from level 3 to go down to level 2 and finally from level 2 to go down to level 1. In all cases, the total energy emitted in the form of electromagnetic energy to go from level 4 to level 1 is always the same. But this means that the electron that is in level 4 has a probability of decaying to level 1, another probability of decaying to level 2, and another of decaying to level 3. These probabilities can be calculated both experimentally and theoretically. To understand these transition probabilities, we will first analyze the radiation-matter interaction mechanisms. Let's assume for simplicity that we have only two energy levels, E1 and E2, with E2 greater than E1. We will see that these two levels can be connected through three radiative processes. An atom at the E2 level can make a spontaneous transition to the E1 level by emitting a photon of energy equal to the difference between the two levels. The probability per unit of time that this process is carried out is defined by the coefficient A2,1, and therefore the number of transitions per second will be A2,1 times N2, where N2 is the number of electrons found in level E2. If the atom is in the lower level and is in turn immersed in an electromagnetic radiation field of density ρ and with the appropriate frequencies, the electron can absorb a photon of energy equal to E2 minus E1 and make a jump to the upper level. The probability of this transition occurring is proportional to the density of radiation B1, 2 per ρ. Finally, if an atom is in the E2 level and in the presence of a radiation density, it can be perturbed by a photon of energy equal to E2 minus E1 and make a transition to the E1 level. Both the disturbing photon and the photon produced by the transition are coupled in phase and direction of propagation. The probability of this transition occurring is B2.1 per ρ. Radiative processes have a probability of occurrence. In the case of stimulated absorption and emission, these probabilities depend on the value of the spectral energy density. The coefficients A2,1, B1,2 and B2,1 are called Einstein coefficients. Although these coefficients depend only on the characteristics of the atom or ion in which the radiative process is established, in a plasma whose atoms or molecules are in thermodynamic equilibrium, it is possible to establish the relationships between the Einstein coefficients. Therefore, we must first establish under what conditions a plasma is in thermodynamic equilibrium. We can say that a plasma is in thermal equilibrium if all the parameters that describe it, both from a thermodynamic and radiative point of view, are represented by equilibrium equations governed by the same temperature T. In particular, in a plasma in thermal equilibrium, the kinetic energy distribution of electrons and atoms is given by the Maxwell distribution. The excitation of the atoms follows the Boltzmann distribution. The balance between different ionization states is given by the Saha-Boltzmann equation. And the energy distribution of the emitted radiation is given by the Planck equation, black body. In thermal equilibrium, each process is exactly balanced by its reverse process, excitation/de-excitation, ionization/recombination, emission/absorption, according to the detailed equilibrium principle. In the two-level system, the exchange of atoms or molecules passing from one level to another is not only carried out by radiative processes but also by collisional processes. Mainly the electrons collide with the atoms that are in a certain level, causing that atom to make a transition to the other level. In this two-level scheme, the time variation of the number of electrons found in level 2 is equal to minus the time variation of electrons found in level 1. Mathematically it is written as the probability of making a transition from level I to level J due to a collision is Ne sig Ni, where Ne is the electron density, sig is the collision transition probability between levels I and J, and Ni is the number of atoms in level I. According to the detailed balance principle, the number of atoms that reach the E2 level through collisions must be equal to the number of atoms that decay to the E1 level due to collisional processes. On the other hand, the number of atoms that radiatively decay to the E1 level must be equal to the number of atoms that reach the E2 level by absorbing a photon. Expressed in equations and taking into account that in equilibrium conditions the number of atoms that are in a certain level is constant, these relations can be written in this way. According to these relations and taking into account that if the plasma is in equilibrium at temperature T, the relation of the population of energy levels will be given by the Boltzmann equation and it will be immersed in a radiation field corresponding to a black. We can see that spontaneous emission is much more likely than induced. For T equals 1000 K it is fulfilled for the optical range, ultraviolet or higher. However, at that temperature, for the microwave region where the photon energy is much less than kT, the stimulated emission can be important. Here we have the relationships between the Einstein coefficients when the system is in thermodynamic equilibrium. It is important to mention that the luminous radiation is the first to break with the detailed equilibrium principle, because the plasma is not completely opaque to radiation and therefore its radiation does not correspond to a black body. If the energy associated with radiation is much less than the others involved, it can be assumed that deviations from thermal equilibrium due to radiation losses do not affect the other thermodynamic equilibria. Under these conditions, the system is said to be in local thermal equilibrium. In a plasma in local thermal equilibrium, the excitation temperature of atoms and ions, Boltzmann equation, is mainly determined by inelastic collisions with electrons and is not greatly affected by energy losses due to radiation. The number of collisions per unit time is directly proportional to the electron density and depends on the temperature. McWhorter's criterion states under what conditions a system is in local thermal equilibrium. Delta E is the largest difference between two adjacent levels. If the plasma is considered thin, that is, photon absorption within the plasma is negligible, then the intensity of a spectral line generated by the transitions between levels Ek and Ei will be given by the probability of spontaneous emission A, Ki multiplied by the number of atoms found in level K. Using the Boltzmann equation to determine the number of atoms found in level K, we have. By applying logarithms to this expression, we get. This expression represents a line in the plane defined by the logarithm of the intensity multiplied by the wavelength and divided by the level degeneracy and the transition probability, versus the energy of the higher level. This plot is known as the Boltzmann plot. From the measurement of the slope of this line it is possible to determine the temperature of the plasma. This procedure can also be used for the determination of the transition probability AKI. Suppose we have a Boltzmann plot generated by the largest number of lines such that the error in determining the slope is minimal. If its upper level and its degeneracy are known for a spectral line, it is possible to determine what value of the transition probability corresponds to it so that the line fits the Boltzmann plots. Another procedure that can be used to determine the probability of spontaneous transition is the branching ratio. According to the expression for the intensity of a spectral line, the ratio of intensities of lines that have the same upper level or belong to levels whose values are very close is. In this case, a relative or absolute value of the transition probability can be obtained if the value of one of the probabilities is known. This procedure implies the very precise measurement of the intensities of the lines as well as a previous analysis if they are not self-absorbed or overlapped with other lines. According to quantum mechanics, the probability of spontaneous transition between levels E2 and E1 is given by the following equation where psi2 and psi1 are the wave functions of levels E2 and E1 respectively. Epsilon 0 is the vacuum permittivity and G2 is the degeneracy of the upper level E2, nu is the frequency of the transition, and M1 and M2 are the magnetic quantum numbers corresponding to the wave functions psi1 and psi2. The line strength is defined as. The Einstein coefficients can be expressed as. By means of calculation programs such as the relativistic Hartree-Fock, it is possible to calculate, among other atomic parameters, the transition probabilities. This requires a deep understanding of the self-consistent Hartree-Fock method and the parameters involved in the entire calculation process, such as direct and exchange integrals called Slater integrals, configuration interaction integrals, spin-orbit parameters, etc. For this reason, it is strongly recommended to study Robert D. Cowan's book The Theory of Atomic Structure and Spectra before starting to use this type of calculation program. The relativistic Hartree-Fock program consists of three programs, RCN33, RCN2 and RCG. The calculation begins with the RCN33 program where the configurations of the atom or ion to be studied are entered. Configurations belonging to one parity can be entered or configurations from both parities can be entered. Electrical dipole transitions occur between configurations of different parities, Laporte's rule. In the slide we see as an example some odd and even configurations of aluminum. From RCN33, the average energies of the entered configurations and the atomic parameters for each one of them are obtained, such as the direct and exchange integrals, the spin-orbit parameter and the radial functions. RCN2 takes the output of RCN33. From this program, the interaction integrals between the different configurations of the same parity are obtained. If configurations of both parities are entered, then the RCN2 will give us the interaction integrals corresponding to each parity and the electric dipole elements between configurations of different parity and that allow the subsequent calculation of the transition probabilities. with the output of RCN33 and RCN2 an input for the RCG code is built. This program calculates all the theoretical values of the energy levels of all the configurations entered and the composition percentage of each level. If the two parity configurations are included, the transition probabilities, the intensities of the oscillators and the lifetime of each level are obtained. The fourth RCE program has as input the known values of the experimental energy levels of the atom under study. Using a least squares process, fit the energy parameters Fk, Gk, and spin orbit and recalculate the new theoretical energy levels. Through the standard deviation between the theoretical and experimental energy levels, the precision of the predicted values can be estimated. Once a good fit is obtained, these parameters are injected into the RCG code and better values are obtained for the transition probabilities and the lifetime of the levels. It should be noted that throughout the calculation process, the parameters can be kept fixed, or they can be released. They can also be scaled by a certain factor. For this, a deep knowledge of the physical meaning of each one of the parameters is necessary in order to correctly decide within which values they can vary within the calculation process. Information about this type of calculation can be obtained from this attached reference. Finally, it is worth mentioning that the transition probabilities are classified according to their precision as follows.